Hi everyone, welcome back. My name is Judith and I'm here to present to you the paper session. That means that we are here presenting the papers that have been submitted to the symposium, peer-reviewed and accepted. And we have 3 speakers today. The speakers will present one by one for 15 minutes and the last 15 minutes will be dedicated to questions for all 3 of them. So if you have a question, please put it in the Q&A and also put there the name to whom the question is posed. So the name of the speaker and then your question. In the chat, I also put the link to where the papers can be found if you're interested in reading them. So now it's time for our first speaker. Our first speaker is Brian Pondi. He's from the University of Münster in Germany. It's nice to see you again, Brian. And Brian is presenting here about APIs for EO data cubes. Brian, the stage is yours.
Okay, thanks a lot, Judith. Yeah, so I think I've been introduced, so I'll just dive in about this vision paper, and it's available online, as already mentioned. So it's standardizing machine learning APIs for observation data cubes. And the flow will be just like on the paper, so definitely a brief introduction, and then talk about the ML API specification, the core components, and talk about a little bit about spatial temporal ML cataloging, consideration, conclusion, then definitely as mentioned, Q&A comes on later. So to be on the same page, definitely the idea of standardization here is to advance reproducibility and interoperability. And in my case, reproducibility here means obtaining same results using identical source code and data. And this is from a paper by Gomez et al. And then interoperability is the ability for 2 or more software components to cooperate despite differences in language, interfaces, and execution platform by Peter Wegner. And then for Art Observation Data Cube, if you've never used it, it's just a multidimensional arrays with a regular spatial and temporal dimension. And for our cases, mostly it's 4-dimension, time, bands, X and Y. And for that case, this is like a simple representation of the Art Observation Data Cube, as you can see, with different time steps, and then you have X and Y with bands. And also this is a different visualization too. And then for the Art Observation Data Cubes, you can do different operations from filtering, aggregating, and more analytics thing. Mostly good for time series analytics, I bet, if you want to do maybe environmental monitoring and things like that. And so definitely in recent years, there's been unprecedented growth of Earth observation or satellite orbiting the Earth, and that also means there's massive data, and also this massive data, there's a wide diverse of users from different countries, continents, skill sets, who have got different resources, access, and that kind of thing. And it's interesting that this paper by Julia Wagman, which is about users of open begat data, analysis of the current state, which I can recommend most of you to read if you haven't. And it basically gives an insight on the various challenges that the users face, especially who deal with the Earth observation. And for data analytics aspects, which is the graph on the right, you can see that interoperability of data and data systems is the leading one. Then there's definitely time series retrieval, is there data discovery, more, and going up to server cloud-based processing. And also for the various data challenges, which include limited processing capability, growing data volume, definitely because of the exponential increase of satellites and orbiting the Earth and providing data, data discovery, and more, lacking easy to use tools and quite more. So definitely right now in 2024, there have been way more developments. There's cloud computing towards this kind of data sets. The concept of cloud optimized geotips or cloud native data sets from COGS and ZAR. And now there's spatial-temporal asset catalogs to make it easy to search and discover these data sets. Yeah. And then this concept of data cube, like there's Xarray in Python, digital cubes in R to manage your data sets once you access them. And also this all these concepts led to a lot of different backend services from Google Earth Engine, Synergize, and quite more. And to unify this, yeah, the OpenEO as a specification came in, and this was started like in 2020. And initially, if you have never heard of OpenEO, initially every user was using their own platform, different code base when they do analytics, right? So if you do, they have to rewrite their code to try out different platform. But OpenEO kind of simplify that. They only have to use their own script, if it's R or Python or whatever, and then they're able to do that. So, yeah. Even though right now OpenEO has existed for about 4 years as a standard and has been adopted now widely, like companies like even IBM, which is now getting deep into geospatial. And there's still a challenge. It really lacks machine learning capabilities, and machine learning are popping up, and there's the new architectures, new foundational model. Even long time the term like the spatial AI was not there, but now it's like really big and things like that. And as you can see, based on just a few sample papers, there are new architectures that come in to help to deal with this kind of data and data cubes like TempCNN or convolutional LSTM, and you can find some of these architectures kind of survive or cloud issues and things like that. So it's nice, but it's only accessible to a limited number of people with who have the skill sets or who can be able to reproduce the model or rewrite and things like that. And the idea is to make it also accessible to a wider audience. And then other interesting papers that I found that talk about future in the Earth observation space, like the paper for artificial intelligence to advance Earth observation, talks about AI interoperability and federated learning and also scalable data processing. But definitely all this will be good if there is an existing ML API specification. And then there's also this paper about ML critical, mission critical, which satellite data is a distinct modality in machine learning. And also another paper about considerations of for AI EU for agriculture in sub-Saharan Africa. And the topics about or components about accessibility to the global and local communities definitely needs standardization, rethinking open science and making it easily accessible definitely comes with the standardization, sharing machine learning models, especially if it's applicable to people with limited resources. Yeah, and also transparency and responsibility being a key thing in science. Yeah, proper specification and standardization helps in this. And for the ML API specification, if you look into it, they definitely came up with like 9 core components that is ideal, and definitely since it's a vision paper, we're even open to more suggestions or ideas. But the key thing is data loading. So from loading up observation data cubes and training data to data preprocessing, whether you want to do aggregation, gap filling, and things like that, temporal aggregation. And for model training, to enable users to be able to pick whichever model if they want to do the classical machine learning or the state-of-the-art new deep learning models. This should be actually possible via a simple API call like MLFit or something. And then ML prediction, which is definitely key. The challenge with again pixels, when dealing with pixel, at times a pixel can have more than one. Let me say, for example, if you're doing a classification, you can have more than one class, and then sometimes this leads to noise. And literature also shows things like doing Bayesian smoothing can help with post-processing. And the seventh one is definitely uncertainty quantification should also be made easier because most of these outputs can be used to make decisions, and it's definitely good to make sure those people involved in the policy or check in your spatial data science analytics to be able to know about the uncertainty of your output in an easy and simple way. And then finally, definitely there's the model saving and model loading. A user needs, once someone has saved a model and we think it can be reused, than it being hidden somewhere or just sitting idle in some S3 bucket or some GitHub that nobody is aware of, or your local computer. I don't know. It would be good to make these models publicly available. Yeah. And then just a simple look into it. That's the rough idea how, for example, you can interact. So in the OpenEO, there are various clients now. Initially, it was R, Python, and JavaScript, and there's Julia. And then can interact with whichever backend that implements the processes, and also to save and load machine learning and deep learning models. Definitely saving and loading machine learning models and making them easily discoverable. It would be good if the community adopts a standardized ML specification. And the good thing is the Stack ML extension, which builds on top of the already adopted Stack extension for the Earth observation community. And for this, you can easily catalog your model and with the relevant metadata, such as the input, area of applicability, the kind of task, and whatnot, and this can easily be adopted. So we wrote a paper about this. It will be in SCM Spatial in Atlanta, but the paper is already online, and if you can't access it, you can look into it. I won't dive into in depth now because that's a topic on its own. But yeah, it's a good thing. So for considerations, definitely we can just talk about standards for ML and also for the workflows. Definitely there also needs to be standards for ML training data, and for this case, there are ongoing works on various. For example, Stack Label, there is the OGC training data markup language, ISO markup language. But definitely the community needs to adopt and start developing tools or libraries or extending this for ease of use and accessibility. Definitely, another challenge is interoperability across ML frameworks and also across programming languages. So, for example, doing random forest in R and saving it might not be easy to use for someone using Python and things like that. So those need to be factored in, and also how to simplify the complex architectures for the planning, so that it's easier for people to use it in simple, like one lines of code and things like that. Definitely model calibration once you think should it be done locally or in the cloud because of the maybe roles pertaining to data they don't want to share or something like that. Handling special geometries is also another key component. Should one do, how do you handle spatial temporal in terms of geometry? There's also this concept of vector data cubes, and also how do you do extraction? Do you do median or whatnot of the values? Yeah, and also currently, as we mentioned, there's a rise of foundational models. I think big one is by the NASA and IBM, but they're quite small models. And how can users easily use these foundational models for downstream tasks? And since this will just be a specification, it would be good to learn from existing frameworks and see how it will be easier to integrate and develop with these frameworks. Into conclusion, definitely the main idea for this is to truly improve the utilization and accessibility of Earth observation data cubes and really driving value from it and doing various kind of analytics that especially that are valuable to policy, environment, and more. And it will be easy again to advance interoperability and reproducibility, and this is actually the goal of the ML specification and standardization. And definitely the other thing is to foster collaborative environment. So when you come up with your the planning architecture, even though it's complex, it can be easier for people. It doesn't mean everyone needs to be an expert, but they should be able to easily use it. Yeah, which again points out to the truly democratization of complex ML architecture. Yeah, and this will be good for all the kind of diverse sets of users that we have, and not only hardcore programmers and things like that. So yeah, to put it short, prototype work is in progress, and definitely ideas are welcome. You can easily contact me, and then you can have during the Q&A any questions that you might raise or concerns. Yeah, that's it. Thanks. Hopefully, I have moved fast, but yeah, yeah, 15 minutes was tight. Cool.
Thank you, Brian. Thanks. Very nicely on time. So as announced before, we'll take all questions at the end. So please put your questions for Brian in the chat. And we'll now move to the next speaker. The next speaker is Mina Karimi from the University of Vienna. Mina is also our technical assistant, so you will now finally see the face that is normally behind the scenes arranging everything. But she's here not for the technical support right now, but to present her research on sense of place. Mina, the floor is yours.
Yeah. Thank you. Hello, everyone, and thank you for joining here on the 5th Spatial Data Science Symposium. I'm just presenting my paper on behalf of my colleagues from the Vienna local hub. We were working on exploring changes in sense of place post-events using large language models. Me, Ivan, and my colleague, also another host, and Krzysztof, Janowicz, the chair of the event, were co-author of this paper. We are working on the Spatial Data Science and Geocommunication Group, Department of Geography and Regional Research at University of Vienna. The concept of place usually goes beyond its geographical boundaries, evolving dynamically in response to some significant events such as wars, disasters, or natural hazards, or some international sports. And these significant events usually shape the societal perceptions. Sense of place, or SOP, refers to the unique emotional and cognitive connections individuals develop with a specific location, which is shaped by its physical characteristic, social dynamics, and also personal experiences. The aftermath of these significant events is often accompanied by notable transformation in how individuals perceive and engage with these places. And the consequences extend beyond the immediate aftermath, which influence tourism patterns and also people's sentiments over extended periods. Effectively documenting these changes over time is critical for understanding the evolution of places. In earlier times, limited access to the internet resulted in less information being publicly accessible about the certain places. However, with the growth of internet and also the social media platforms, a lot of information are coming behind numerous places, and this information are publicly available, although not all of them are actively utilized by individuals. Exploring variation in the sense of place has been studied in literature using questionnaire or social media contents, but still there is a notable gap in scholarly research that systematically analyzes the evolution of sense of place over time. While questionnaires demand substantial resources in terms of time, finance, and effort, both questionnaires and social media contents not able to capture sentiments before, during, or after some past historical events. For example, Chernobyl, the nuclear disaster in Chernobyl. Specifically, this would raise some issues when these historical events have happened. On the other hand, with the growth of generative AI, or particularly large language models, we could see more attention in recent years in these advanced models. These models, which are exemplified by ChatGPT, for example, have remarkable capabilities in generating text and images from some prompts using some natural language queries. While it is not possible to go back and do some three questionnaires about how people perceive Chernobyl before, during, or after the catastrophic event about the explosion of the nuclear reactor. We can ask LLMs to generate these contents from the vast amount of data and knowledge they have. For example, these online contents that they have access to. This underscores the apparent value of generative AI capabilities in such endeavors. So we here try to come with this gap and try to understand the potential and effectiveness of large language models in identifying the shifts in sense of place, which are followed by some significant events. And we aim to assess how ChatGPT, for example, explores changes in sense of place and their implication on people perception after these significant events. To do this, we first of all try to collect our data sets. We use some ChatGPT prompts to generate some description of places over time. We use this prompt, for example, describe with one paragraph for each year, how did people perceive a specific place in different time zones, 10, 5, 1 year before the event, during the event, and 1, 5, and 10 years after the event happens. And place here are different 5 places that we try to discover during the study. And we put months and year for our time, and the others are the shifts from the offsets from the events in years. We also try to use another prompts, again from ChatGPT, to produce 5 keywords. These keywords will describe the sentiments of paragraph response by the first prompt that we showed before. The second prompt was express the sentiment of each of the following paragraphs using 5 words. And finally, we did sentiment analysis on both keywords and full paragraphs generated by ChatGPT, and each prompt answer is analyzed individually and represented with a polarity scores, -1 for negative, 0 for neutral, and 1 for positive emotions and sentiments. We tried to come up with 5 case studies examining places such as Hiroshima, Chernobyl, Paris, Wuhan, or South Africa in different time zones with different events. For example, atomic bombing in Hiroshima in, about more than 70 years ago in 1945, or nuclear disaster in Chernobyl again in 1986, many years ago. And also some recent events with terrorist attacks in Paris in November 2015, and COVID-19 outbreak in Wuhan in late December 2019, and also FIFA World Cup in South Africa in 2010. The paragraphs that we produced were a lot to show, but now we only show the keywords generated by ChatGPT for 7 different time zones that we selected, and also 5 case studies that we exemplified. Here you can see that it creates some keywords. For example, for Hiroshima, some catastrophic keywords after or during the event. Or for Wuhan, before the COVID, it was a kind of industrial and educational destination, but during the COVID-19 outbreak and immediately after that, it was just kind of symbolic for some pandemics. We did also sentiment analysis on both keywords and paragraphs. You can see that for the 4 of our events, we had negative responses and a shift on people's emotion during the event and some years after the event, but again try to come back to their previous versions. But for South Africa, it was completely different. During the event, people had more positive emotions based on ChatGPT textual data. Here you can see also the results of our study only for keywords, and it's notable that generating keywords could took us more results, more words that can clearly specify the events aftermath, some significant emotions after these events or before them. What we could find from our observation was that before the tragic events such as Chernobyl, Hiroshima, or Wuhan, sentiments were distributed across positive, neutral, and negative categories, indicating a balanced perception of these places. But tragic events saw sharp negative sentiment shifts during or immediately after these events, reflecting the profound impact of this event on people's perception. Also, we could see the positive shifts for FIFA World Cup in South Africa, showcasing the transformative power of international sporting events in shaping positive perceptions. Also, we did some comparison between keywords and paragraph and showed that keywords provided a stronger polarity, positive or negative extreme compared to full paragraphs. We had some different limitations. For example, there are many local and international examples with different effects on various regions, which are not considered in our study. Also, these percentages are estimates and may vary based on interpretation. And the other limitation was that sentiment analysis is usually subjective and can be influenced by context and individual perspectives. To conclude our research, we want to mention that we used LLMs to investigate the evolution of sense of place over time, revealing the impact of significant events on perceptions. And we found that these significant events drastically alter sense of place, and tragedies result in lasting negative sentiments, while positive events like FIFA World Cup can improve perceptions temporarily. And also, we could see that there is insights for researchers, policymakers, and urban planners to address post-event perception of places. And as the future research suggestion, you can work on comparing the LLM-generated sentiments with some human-based surveys or some social media contents, similar to what Bernd mentioned in the workshop for validation. And also, definitely you cannot use this for some very old events, but for the recent one, with benefits from social media, it's possible. And also examine the same event in different locations, as we believe that the sense of place after FIFA World Cup in Germany and South Africa are not really same. And you can also borrow the application for using LLMs to explore sense of place across more regions and events time, and also investigate the local and global effects of these events. Thank you very much.
Thank you very much, Mina. Also nicely in time. I already see some questions for Mina in the chat. Please post your questions there. Then we move to our final speaker, Anuj. Anuj is from the University of California, San Diego, and he will present to us about epidemiological simulations. So since this is into my research area, I'm very much looking forward to this talk. Anuj, the floor is yours.
Hey, hi everyone. So my name is Anuj Goenka, and today I'm excited to present our research on how large language models, or LLMs, can support spatially disaggregated epidemiological simulations. So we have been exploring their potential to make public health decision-making more specialized and effective. So we know epidemiological models like SEER help predict how diseases spread, but they usually are too broad to account for local variations, things like population density or healthcare access. That's where spatial data comes in. Our question is, can LLMs adapt these SEER models to provide more localized insights? If we can use LLMs effectively, they might help make public health decisions more tailored to specific areas, which is crucial during outbreaks. So the dynamics model that we are using was a serious game for pandemic preparedness to test public health interventions in a dynamic way. There were teams of health professionals, officials, researchers in San Diego that had to respond to a simulated disease outbreak, and they were given something called game units representing resources and had to allocate them to strategies like contact tracing, public health messaging, and improving healthcare systems, among others. And the judges then mapped these decisions to a system dynamics model in Stella, which simulated the outcomes. The model itself is complex with over 800 stocks, flows, and converters representing different infection stages and age groups. While it was flexible enough to handle future outbreaks, one limitation was that it didn't include spatial data. And it is critical how populations and healthcare access vary across San Diego or any region for that matter. So for our experiments, we used COVID-19 data from San Diego County and applied the SEER model to each zip code. Initially, we tried using Python libraries like PySD and PPTKPy, but they couldn't handle the model's complexity, especially some Stella-specific features like conveyors and dimensions. So we re-implemented the entire model in R and accessed it through Python using RPy2. This allowed for like dynamic updates. We also added a retrieval augmented generation system, also called as RAG, system to pull in spatial and demographic data like zip code boundaries, healthcare locations, so that LLMs could give localized public health recommendations. We used two LLMs, namely Llama 3.1, the 70 billion parameter version, and the Mixtral 7 billion parameter version. Both of these were accessed through an API at San Diego Supercomputer Center, which was able to handle large token capacities that we had and communicated smoothly with our model. We designed our experiment by asking the LLMs to allocate 10,000 resources or game units across different zip codes in San Diego. The LLMs used their knowledge along with the data that we provided through our RAG system. And this included demographics, healthcare facilities, neighborhood info, all of these. But initially, we only focused on 3 zip codes to test all of the experiments that we did. The 3 zip codes were mainly the downtown San Diego region, which had highly diverse population, the Rancho Santa Fe region, an affluent area that had an older population, and the UCSD, my university itself, which is predominantly students. We picked 3 zip codes, these 3 in specific due to the compute costs, like running all the experiments for all the 113 zip codes that we had for San Diego would have been too expensive. So these still gave us a good range of spatial and demographic contexts to work with, and helping us see how well the LLMs could adapt to the strategies. For our first experiment, we tested how well the models handled the zip code 92093, the area of my university itself. When asked about it in GPT-4, it was able to recognize that it was a university campus with a student-driven population and research facilities, showing how strong the spatial reasoning and contextual understanding of it were. As you can see at the very top, that's the ChatGPT, and the bottom one is Llama. So it was a little contrasting, which gave more generic information, focusing on basic details like location, housing costs, but missing the key point that it's actually a university's zip code. So this highlights a major gap in llama spatial awareness and its ability to or inability to adapt recommendations based on the area specific characteristics. So while GPT-4 can tailor responses to unique needs of a university area, Llama 3 would have tended to provide more surface level answers. The second experiment, we aimed to see if LLMs could allocate resources effectively over multiple SEER model stages while dealing with some real-world constrained scenarios. We let the LLMs itself figure out the stages based on the SEER model output, but both Llama and Mixtel had some trouble managing resources across the stages. We allocated the budget of 10,000 units, if you remember, but they often overshot the available resources, struggling with like cumulative limits, uh, even after tuning the prompts. Yes. So another challenge was balancing the spatial data, like healthcare facilities or neighboring zip codes, among the other factors. Their recommendations were often too generic, especially Mixtel, which couldn't handle the complex relationships between healthcare, demographics, and spatial context. Although this time we did see some improvements with prompt tuning for the balancing of spatial data. So we guided the models to review and use all the data. However, fully integrating spatial data still remained difficult. For the third experiment, we wanted to see if LLMs could infer neighborhood relationships or if we needed to provide that information explicitly via a contiguity graph. The results shows that it highly depends. The llama produced more nuanced resource allocations when given explicit neighborhood data, adjusting strategies more effectively. Especially, you can see that in zip codes 92101 and 92091, there are similarity scores when compared without with inferred versus explicit. The similarity scores dropped to around 70 and to 76%. This means that llama took neighboring areas into account better with more information. On the other hand, you can see Mixtel's resource allocation were much more consistent, staying between 88 to 90%. Whether we give it explicit neighborhood data or not, it didn't really use the spatial information as much, relying much more on its internal reasoning. So even though providing the contiguity graph improved the model's ability to take broader relationships into account, they still missed an important detail in some cases. So as you can see at the right hand side, I show you a map. So we were expecting that if for zip code 92093, which was the UCSD zip code, we were expecting it to see that there is a Jacobs Health a research facility or a really big healthcare facility nearby, but it completely overlooked that. And despite having access to this explicit spatial information, the models recommended unnecessary investments in healthcare facilities within the 92093 zip code itself. So this highlights that while the models showed some cross-border awareness, they still struggle with fully incorporating critical spatial data in certain scenarios. Ultimately, Llama benefited more from explicit spatial data, while Mixtel showed less sensitivity. So for the fourth experiment, we wanted to see how consistent the Llama LLMs are in their allocating resources over 100 runs. So we tested Llama and Mixtel on same strategies like widespread testing, social distancing, healthcare facilities, among others, and across 3 zip codes. The table shows that average allocations and the range of variability for each strategy. One key takeaway was that Llama, being a larger model, had much more variability in its output. For example, in zip code 92093, the range of Llama's allocations for public health campaigns fluctuated by almost 200%. And this high variability reflects its adaptability, but it also introduces a lot of uncertainty. Mixtel, being smaller, was much more stable. Its allocation barely changed across runs with little to no variation. For instance, in the zip code it allocated 1,000 units consistently for social distancing without any fluctuation. So while Mixtral is more predictable, it's also less flexible when it comes to diverse scenarios. So in summary, Llama's variability gives it ability to provide more nuanced solutions, but at the cost of consistency. While Mixtral offers a more stable but perhaps less dynamic recommendations. In the first round of experiments, when we wanted to generate allocations for all the zip codes in the San Diego region, Llama's resource allocations seem to follow a reasonable pattern based on the context of zip codes. The explanation provided by LLM was that certain areas lacked healthcare facilities and even neighboring zip codes had few resources available. So this led to higher resource allocations in these regions, and which made sense because when considering their geographic and healthcare contexts. And these allocations aligned with the demographic data that we had for these regions, suggesting that Llama did recognize the spatial gaps. But to be sure with that these patterns weren't just a fluke, we ran an experiment multiple times to check if these trends held up over several iterations. Let's see what happened next. After running the multiple iterations, the clear patterns we saw earlier started to fade. We initially thought were what we initially thought were well-informed decisions now seemed less reliable. So some patterns might still be explained by the factors like population vulnerability or healthcare processes, but many allocations appear random or spurious, which we are referring to as hallucinations. And these cases where the model generates allocations where without truly understanding the spatial relationships. It's now clear that the strong patterns we saw earlier were likely coincidental. When averaged over multiple runs, the LLMs actually struggled to maintain a consistent spatial reasoning, suggesting that the initial results were more about randomness than informed decision making. So our experiments showed that LLMs hold potential in spatially disaggregated simulations, but their performance varies significantly across models, regions, and resource allocation strategies. The results improved when we provided explicit spatial data, such as the contiguity graphs. But this helped the model also get better coordinate resources across zip codes. However, a key challenge remained. Managing resource allocations across multiple stages was still problematic. The model struggled to adapt to real-world cumulative constraints, which often led to resource overshoots and inconsistent recommendations. Another major issue was their inconsistent spatial understanding, especially in recognizing neighborhood proximity or cross-boundary resources. For instances, in one of our UCSD tests, both model completely ignored the nearby healthcare facilities, leading to resource misallocation. We also encountered hallucinations, particularly with Mixtral, where the models made irrelevant or incorrect recommendations due to the misunderstanding of the spatial relationships or lacking just local knowledge. Lastly, while GPT-4 and Claude 3.5 performed better overall for location-dependent tasks, they just come with higher costs and token limitations, making extensive use of RAG really challenging in those scenarios. So in summary, LLMs do show promise, but there's still work to be done to refine the spatial reasoning, improve their ability to manage complex resource allocation over time. Looking ahead, one of our primary goals is to enable dynamic scenario adjustments using a Python orchestration layer. So what this will do is it will allow the to query LLMs at key decision points during multiple runs of the simulation. And it will enable real-time scenario updates and more adaptive decision making. We are also focused on incorporating more sophisticated spatial data sets to improve the model's spatial reasoning. For example, we have a Sandbags transportation model, which simulates flow across 4,500 plus MGRAs in San Diego, and it could add important context around population movement and how it affects the resources needed. In terms of improving the model performance itself, we plan to fine-tune the LLM prompts to make to be more task specific by narrowing down the focus of each prompt, we expect to see better accuracy without needing extensive model fine-tuning. And lastly, we aim to experiment with larger llama implementations like the 400 billion parameter version, which could improve the model's capacity to manage complex spatial data and the resource allocation strategies. Thank you. We're open to questions, I guess.
Yes, thank you too. So now all three speakers are back on stage, and we'll go ask questions to all of them. We'll start with this first question for Brian, asked by Simon. To share machine learning models catalog, you need to know its purpose. There are no purpose-free models. How does your API take purpose into account?
Okay, thanks, Simon, for the question. Definitely to save the ML model, as I mentioned, there is the stack ML specification. And for this, it specifies various key attributes that are necessary, or metadata that are mandatory. For example, the inputs or the accelerator, the components that were used, and things like that, which this can kind of automatically be inferred. But for the task, there's also a variable for the task, which is mandatory required, and this can be classification, regression, it's an enum of list, similarity search, or whatever. So when the user is clicking, assuming, for example, the API is save ML model, then they need to pass the purpose or task, in this case, as we call it, on what kind of task can this model be used for. And that's it.
All right, thanks. So questions are still welcome, especially from people other than just Simon. I'll next put a question on stage by Bruno, and it's for Mina. It's about representativeness. So isn't use of LLMs as a replacement to surveys very risky in terms of only reflecting or even reinforcing common stereotypes? Could you reflect on that, Mina?
Yeah, thank you, Bruno, for your nice question. Yeah, I agree that at this stage, it's not really a complete replacement. LLMs are not really complete replacement of surveys or social media contents, but we are just going to this I think in the next few years, but we can do some. We can have some ideas to ensure that LLMs can produce results that represent diverse views and also minimize the risk of reinforcing these stereotypes. For example, we can just try to train using different and diverse training data sets, which are representative for all kind of, for example, cultures, geographical or ideological backgrounds. This can ensure that this representation from different communities can help to create a more balanced output. Or, for example, we can also this is the challenge that recently LLMs are dealing with, the biases and the different kind of biases they have. But training on different data sets maybe would be another a good solution. Also, I think prompt design and contextual framing of this prompt would be really important, and maybe we need to think about how we can design our prompts more diverse, or adding some context to our prompts to be sure that it's dealing with different biases, political, socioeconomic, and cultural biases. Maybe also another solution can be fine-tuning and using some human feedbacks to incorporate and know different groups of human reviewers to maybe include their comments, their suggestion, or their feedbacks. Yeah.
Yeah, good. I think that's a very complete answer. Thanks, Mina. And I think it's also a nice bridge to the next question that I'd like to put on stage, which is originally to Anuj, and I'd like to ask him first to answer, but I think maybe all three authors could reflect on this. So what is the method for validating the allocation results of the model? And I think the same question could be answered to Mina. So how could we validate the sentiments that the LLM is giving? So Anuj, would you like to comment on this first?
So that's why we actually tried to use something that we already knew about, like focused on a region of San Diego itself. So we evaluated where the resource allocation patterns were actually made. It actually made spatial sense and were actually appropriately prioritized. For example, we compared that zip codes with fewer healthcare facilities were expected to receive more resources for public health campaigns and testing initiatives. So that's the reason why we chose San Diego itself. And other than that, we did try some quantitative comparisons, like using the similarity scores across the runs and calculating the range percentages for all of the quantities that we had, also the contiguity graphs that we had, and uh, mostly it was like a real world contextual relevance that we were actually looking for. So we cross validated the model's allocations with real world needs and drawing on like expert input and public health guidelines. Uh, like for example, we use the national COVID-19 preparedness plan to see what were the strategies that were recommended. So I guess that was for that. And if you want to know how the allocation was actually good, uh, we just see that how they align with real world context of the region. They prioritize risk areas effectively. Um, Perhaps demonstrated consistency across multiple runs. Uh, they were able to incorporate the spatial data that we provided them, like the neighboring zip codes, appropriately. And yeah, yes, I hope that answers your question.
But this is basically an optimization problem, right? So comparing to the real world, I mean, what happens in the real world is not necessarily optimal. So does that validate your approach then?
I hope it does, but mostly it's about just using expert recommendations or cross-validating that with the model's allocations. Other than that, we haven't really have provided something that will actually verify the application.
Okay. Would any of the other two authors also like to reflect on this question more in general about the validation? Maybe Mina?
Yeah. I also wanted to mention that maybe at this stage we can use some social media contents, for example, tweets that people just post during the event or after the event or before that for specific locations, and we can just compare our results with those in the social media contents, for example, in X or formerly Twitter. Would be a solution, but as I mentioned, there is a gap, and we cannot do this for some historical events such as Chernobyl, and I couldn't find any real idea about validating these events. But for the recent ones, I think it would be great to also check the sentiments with some social media content. Also, I think questionnaire would be also another solution that we can go and ask people when they are thinking about, for example, Wuhan, what comes to their mind. But this is another challenging that we have. We can't go back and ask their emotions about Wuhan before COVID-19. What we can hear is from this point of view, not really, for example, 5 years ago.
Good. Yeah. Yeah. Thanks. Brian, any response from you? Or is this not so much related to your work?
I don't think it's related.
Okay. Let's see. Then maybe let's move to this question. Can the authors talk more about the relevance of these results? So what kind of decisions do they support? Can I give the floor to anyone?
Can you please mention the question?
The question is, can the authors talk more about the relevance of their results? So what kind of decisions do they support with this work?
I think in terms of if I want to mention about our research, I can explain it has also benefits from, for example, decision makers or urban planners, that they can, for example, after some significant events, for example, we had Olympics in Paris, and they want to arrange too many things, and how many people are going there, and then after this event, what was the emotion of people, and then sense of place, whether it changed the sense of place regarding Paris after these international sports or not, or in terms of tourism, how many people would come back or are willing to go to this place after this event. I think would be another benefits from tourism sites.
Okay, on my end, I think I mentioned mine during the presentation, but basically for the ML APIs standardization, it's definitely to make it easier for different audience with different skill sets to be able to use the complex machine learning deep learning architectures for various problems that exist or that they can use, and also the capability of sharing and reusing models. Yeah. Especially in the global south. Yeah.
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 For me, I think it's the most important. It's what we are actually working on. So LLMs would be how they would assist in like the decision makings, and by analyzing all the insights that we give them. For instance, in public health, they can support the decisions on like resource allocation during any disease outbreak or anything by suggesting where to focus the testing efforts itself, or how to distribute vaccines for that scenario. So just basically which areas require more healthcare infrastructure based on the population density, vulnerability. And in terms of the policy, it can guide many policy measures like social distancing, public health campaigns. We just have to put that in the preferred strategies for the LLMs, and I guess they can help policymakers quickly evaluate a wide range of scenarios. Yeah.
Good. I have to interrupt you here because we have to round off the session. I'd like to thank all three speakers again, and also all people who asked questions and thereby facilitated the discussion.